Hello, welcome to the Quality Improvement in Math Education project. This project is initiated by IIT Bombay and Rashtriya Madhyamik Shiksha Abhiyan. It has been guided by Professor Inder K. Rana sir, IIT Bombay, and Professor S.J. Garpure from IIT Bombay. This is video-based PPT presentation. My topic is chords of circle. My name is Amita Patel. My registration number is MTE013 and my school name is Sri S.K. Somaya Vinamandir. It is in Mumbai North. This presentation is based on 3 steps: observe and explore, define and prove, and apply and evaluate. Observe the figure. You can see that this figure shows equator, North Pole and South Pole, and the horizontal line shows the latitude of the Earth. This figure is 2-dimensional, assuming Earth is spherical. Here in this picture you can see that vertical strips are there of different colors. Imagine a line segment between the two regions which separates the different color strips. Now we'll see some of the polygons. Here in this picture you see a circumcircle of a triangle. You observe that vertices of the triangle are on the circle and the sides of the triangle are in the interior of the circle. Same way in a cyclic quadrilateral, also you find that the vertices are on the circle and the sides are in the interior of the circle. Let's see more of the polygons. Polygon with 5 sides is called pentagons and polygon with 6 sides is called hexagon. The polygon with 8 sides is called octagon and polygon with 11 sides is called HENDECAGON. Now let's see some of the archaeological structures. In this archaeological structure we observe that the design in circle or circular arcs are of the more importance and they are immensely used in archaeological structures. Nowadays also we find that semicircular arcs are used as an entrance which adds to the beauty of the structure. We also see semicircular kneaded piece. The pouch is also of semicircular region, and the steering of the car, you see that there is a horizontal line which divides a circle into 2 parts. Each part is called semicircle. And in this figure you see green color and yellow colored semicircles. If we cut the circle through the diameter, we get 2 semicircular regions. These are also some circular objects. The cake and pizza in this, you observe that they are cut through the diameter and they appear to be somewhat triangular in the shape. This is a pie diagram of cost, showing the cost of education and living and the morning sales. Pie diagram is a circular diagram showing the sector, illustrating the proportion, and the arc length is proportional to the quantity shown. Here you can see there are 2 wall clocks, circular in shape. Comparing this with the parts of circle, in the first circle, we observe that the needle of the clocks are representing the radius of the circle, whereas over here in this we find that this looks like diameter of the circle. Now we compare the two circular regions in the way they are cut in the manner. We see here that the cake is cut through the diameters. There are 4 different diameters are drawn and the 8 pieces are made. If we cut this figure then through the equator, then we'll get 2 semicircular region. Now here you observe is a pie diagram. In the pie diagram, this triangular regions or the sectors are not equal in proportion, and we see that each of them has got triangular shape with having 2 sides as the radii of the circle and the arc lengths. Over here we see the purple region, which is separate. Purple region is a circular region separated by the line segment drawn between the yellow region and the purple region. So this purple region, we can say that it is the circular region part, which is also called segment of the circle. Here are the 2 different diagrams of bow and arrow. In this diagram you see that the bow and string are making the circular region, and over here the string is stretched and forms a circular region. Now let's recall the same shape. In the circle you find that the needles of the clock are forming triangular shape. Over here in cake also you find there are triangular shapes are there. Same in pizza, and here also in pie diagram you find that triangular regions or the sectors are made. Here we see that the different regions are made by the line segment which is drawn. So each of the line segments divide the circle into 2 parts, may be equal or may not be. Over here, if we cut through equator, we get 2 equal parts, but if we cut through any of the latitudes, we'll be getting 2 circular regions. In the circumcircle also, the sides of the triangle is a line segment which divides a circle into 2 parts which are not equal. But over here this needle acts as a diameter and makes the 2 equal parts of the circle. Define and prove. Let's define what is the chord of a circle. The line segment joining the 2 points on the circle is called chord of the circle. Do you know why this line segment is named as chord? You can see that the bow and the string and this circular region are forming, they resemble each other, and we can compare the chord of a circle with the bowstring. And in Latin, the bowstring is called as chorda. From that chorda, a letter is dropped and it was named as chord. The strings of violin and guitar are also called as chords. Now let's see that when a chord is drawn, it divides the circular region into two parts, which is called as major segment and minor segment. And it divides the circumference into two parts, that is major arc and a minor arc. Here we can see sectors and segments. This is minor segment and the remaining part is a major segment. When a longest chord is drawn, that is diameter is drawn, it divides the circle into two parts and each part is called as semicircle. The sector is part made by the two radii and the length of the arc, which is somewhat triangular in shape. This part is a minor sector, whereas this is called as major sector. Properties of chords of circle. There are many properties of chords of circle that we have to prove. That is, perpendicular drawn from center to the chord bisects the chord. Equal chords are at equidistance from the center of the circle. Central angles subtended by congruent chords are equal in measure. Corresponding arcs of congruent chords are equal in measure. And the intercept made by intersecting chords are in proportion. Before proving them, let's find out what is the distance of a point from a line. The line is given and a point A is given outside it. Take the different points B, C, D, E, F on the line and join them with the point A. We find that the chord, the segment AD is the shortest line segment, which we consider as a distance of a point from the line and which is always perpendicular to the line. How do we find the distance of chord from the circle? Now, when a chord is given, we draw perpendicular from the center to the chord, which is the distance of the chord of the circle from the center. We can find the chord length is equal to 2 into root of r square minus d square using Pythagoras theorem. Properties of chords of circle. Perpendicular drawn from center to the chord bisects the chord. Here you observe that chord AB is there and OC is perpendicular to the chord AB, and we can prove triangle OAC and triangle OBC congruent by hypotenuse side theorem, and therefore we can say AC is congruent to BC, which shows that it bisects the chord. Similarly, converse of this theorem can be proved. Equal chord theorem. Equal chords of a circle or congruent circles are at an equal distance from the center. Observe the diagram. AB and CD are the congruent chords. We have to prove that the distance from the center, that is OE and OF, is congruent. We can show the triangle OEF, OEB and OFC congruent by hypotenuse side theorem, and after proving that we can show that OE is congruent to OF, which are corresponding sides of congruent triangle. Angle AOB and angle POQ are central angle formed by the chord AB and chord PQ. These chords are congruent. We have to prove that angle AOB is congruent to angle POQ. As we know, OA, OB, OP and OQ are the radii of the circle. We can show that triangle OAB and triangle OPQ are congruent by SSS test of congruence, and therefore angle AOB will be congruent to angle POQ as corresponding angles of congruent triangle. Intersecting chords. The chords of the circle may intersect in the interior of the circle or in the exterior of the circles, but the intercepts made by them are in proportion, that is PA is to PC is equal to PD is to PB. Ultimately we can say that PA into PB is equal to PC into PD. Angle subtended by chord. Central angle subtended by a chord is double the inscribed angle in the same arc. A is inscribed angle and 2 is the central angle, which is the double of the inscribed angle in the same arc, same segment, sorry. Angles subtended by a chord in the same segment are congruent. So here you have angle BAD and angle BCD are congruent. Apply and evaluate. Chords in trigonometry. Chords were extensively used in early development of the first known trigonometric table compiled by Hipparchus. He is the father of trigonometry and the Greek astronomer who mapped the position of about 850 stars. He tabulated the value of chord function for every 7.5 degrees. Hipparchus. What is a chord function? The chord function is defined as the chord of an angle, that is the length of the chord between the 2 points on the unit circle separated by the angle. The chord function can be related to the modern sine function, and chord length RCRD theta is equal to root of 1 minus cos theta the whole square plus sine square theta, that is equal to root of 2 minus 2 cos theta, that is equal to 2 sine theta by 2. Application of chords in the real world. The circular arcs turn up frequently in the real world, such as top of the window on the right. When constructing them, we know the width and the height of the arc and require to know the radius, and the formula for the radius is h by 2 plus w square divided by 8h, where h is the height measured at the midpoint of the arc base and w is the length of the chord defining the base of the arc. Here we observe, if we have to build a bridge on the river, we know that length of the river is 66 meter and the height of the circular arc drawn is 12 meter. Then we find that the radius of this circular arc is 51.375 by the same formula, h by 2 plus w square divided by 8h. This is the archaeological structure, that is theatre in Spain. This theatre was built in 1905. It hosts many plays and concerts. It is an excellent example of circles in architecture. Here you can see 5 windows are there. All the circular arc are of 240 degree and the each chord, that is called golden chord, is connected to the rectangular base that connects the rectangular base to the circle. Here we can see that the geometrical design is drawn. You know that this is the square inscribed in the circle, and you know that sides of the squares are equal and they are equidistant from the center. Knowing this, we can create such designs. Evaluate. A boy was drawing a circle. He drew a part of circle and he went out as his friend called him. He came back and wanted to complete the circle, but he could not locate the center of the circle. How can you help the boy to locate the center of the circle? To locate the center of the circle, draw two non-parallel chords in the arc drawn. Draw the perpendicular bisector of the chords, and the point of intersection is the center of the circle. Using this center, he can complete the arc, complete the circle. Here in this figure, you have been given that chord AB and chord CD are of equal length, and the distance is shown as 2x plus 6 and 24. You have to find the value of x, and if AB is 36, what is the radius of the circle? Using the property of equal chords are at equal distance from the center, we know that 2x plus 6 is equal to 24, and we get x equal to 9. Secondly, the perpendicular drawn from center to the chord bisects the chord, as AB is 36, half of AB is 18, and using Pythagoras theorem in a right angle triangle, we can find the radius of the circle to be 30 centimeter. Let's solve another problem. Using the property of intersection of chords, here the data is given. You have to find the value of x. So as we know, these are intersecting chords. We know that x plus 2 into 8 is equal to x into 12. And solving this linear equation, we get the value of x equal to 4. In this sum, you have been given that ABCD is a isosceles trapezium, and the arc length AD is 80, arc length AB is 16. You have to find the arc length DC, that is x. Knowing the property that in an isosceles triangle, the non-parallel sides AD and BC are congruent, we know that corresponding arc AD and arc BC will be congruent. Therefore, arc BC is equal to 80 degree. And knowing the another property that the sum of the arcs of the circle is 360, we can find arc DC is equal to 140. Here you have two chords AB and CD which intersect at point C. The arc intercepted by them is BD is 70 and AC is 170. You have to find the value of x, that is angle BED. Now, knowing the property of intersecting chord, when they intersect in the interior of the circle, angle BED is equal to half the measure of sum of arc BD and AC. That is half of 70 plus 170, that gives you half of 240, and x equal to 120. Thank you.